So now we're almost going to take a step back in history almost and look at the concept of electric fields, and in particular focus on this force field model versus the action at a distance model. So we've just looked at Coulomb's law and the idea that two forces that aren't in contact with each other can exert a force on each other. And before that we looked at gravity and the idea that two masses that aren't in contact with each other can exert a force on each other. But if we just think back in time 200 or 300 years when these theories were being developed, people were really not comfortable with the idea that two objects that were not in contact with each other would be able to exert a force on each other. This was a time before, mobile phones and radio and even telephone and all these things that we just take for granted these days, where we can actually communicate across, huge distances. Back in those times, if you wanted to send a message to someone, you actually had to physically send a letter. You had to actually physically send an object to transfer. So this idea to people 200 or 300 years ago that forces not in contact with each other, what we know as the action at a distance model. So action at a distance, i.e. two things that are not in contact, so they're a distance apart, can actually exert a force, so an action on each other, was just counterintuitive. People weren't happy to accept an explanation that went against what they inherently felt. And remember, all that really a scientific theory is it explains something that we can observe. So, if you can't picture in your mind things at the idea of forces exerting or objects exerting a force on each other without being in contact, that theory wouldn't have seemed very satisfactory. So the solution to that was to come up with what we call the force field model. So what the force field model says is that, and we'll concentrate here on the electric field, that a charged object has an electric field that surrounds it. So it has this force field that surrounds it, much in the way that we might think about, a kid's cartoon character or a kid's a game character, having a force field to protect it. The Mario force field type example. So they decided that these things must be surrounded by fields, which are almost part of the charge. And then when something entered that field, it interacted with the field rather than interacting with the actual charge that it wasn't in contact with. As I said, nowadays it doesn't seem necessary, and it seems almost a bit counterintuitive because we're so used to things being able to, communicate, act on each other remotely. So let's look at how we formally define what an electric field is. So if we have a charge here, Q, and we want to know about the force experienced at this point here by another charge, which we've called little q, we need to know about, in the force field model, what is the electric field strength at this point. And the electric field strength is defined as, E is firstly what we use for electric field strength, and that is equal to the force per charge at that point. So the electric field strength at the point here is defined as the force per unit charge at that point. So electric field strength, when we're talking about charged objects, is very similar to acceleration when we're talking about gravity. If we use Newton's second law, we can state that as the acceleration is the force per unit mass. If you rearrange that, you get back to the F equals ma form of Newton's second law that you're more familiar with. But acceleration So how much acceleration you experience due to gravity is defined as the gravitational force per unit mass. Electric field strength is the force per unit charge. So you can see there's a lot of similarities in terms of electric field strength and acceleration. Now, if you remember, we worked out what the acceleration due to gravity was by basically equating Newton's second law, back in the F equals ma form, with the force due to gravity being equal to g m1 m2 on r squared. And we do a similar thing here to work out the actual electric field strength due to a charge q. So if we want to know what's the field strength at this point here, r meters from a charge q, we can do, and this is basically we're doing the, using Coulomb's law, derive this expression for electric field strength. So just in terms of our intended student learning, this is the space we're in. So if we rearrange that definition for the electric field strength, we get force equals EQ. And we know that also for electrostatic force, the force equals 1 on 4 pi epsilon naught times by Q times Q. So we're dealing with this two charges up here, so we'll keep that notation, divided by r squared. So that means EQ equals 1 on 4 pi epsilon naught times by Q, big Q, times by little q, divided by r squared. We can see here that those two q's cancel, and we get left with our electric field strength equals 1 on 4 pi epsilon naught times by q over r squared. So what we've just shown there is our derivation for Coulomb's law. We know from this definition how to define the electric field strength. We've talked about this idea of the action at a distance model. And finally, you need to be able to solve problems, which is very similar to the way we would use Coulomb's law with this electric field strength derivation. So yeah, that's, if you like, our introduction to electric fields, plus our derivation for how we work out the strength of an electric field. I'm now going to go on and look at the electric field in some different scenarios. So let's look at how we represent the shape of an electric field due to a charged object. So if we have a negative charge, how do we describe the electric field that surrounds that charge? So the way that we do that, so what we've got to do this initially for is just sketch the electric field lines for an isolated positive or negative point charge. So an electric field can be represented by field lines such that the direction of the field is at a tangent to each line, i.e. the direction the line pointing is the direction of the field, and the magnitude of the field at any point is represented by the number of lines crossing a unit area perpendicular to the field in the vicinity of that point. So that second statement there is a really, so basically I'm talking about this part here in yellow. If you want that in common language, that basically is the closer together the lines are, the stronger the field. So when we define electric field, we always do it for a positive test charge. So if we put a little positive test charge there, what would be the direction? Well, positive would be attracted towards negative, so it would be getting pulled down towards that charge. When we draw electric fields, really, really important, electric field lines meet a conducting surface or meet a charge at 90 degrees to the tangent, so perpendicular to that line. Once again, if we were down here, the charge is going to get pulled up directly towards that charge. So if we can sort of expand that out, this is what the field would look like surrounding an isolated negative charge. And so that thing I said before in the yellow, the number of lines crossing a unit area perpendicular to the field, basically, obviously when we're closer to the charge, the field is stronger. The lines here are closer together. As we get further out, the lines are further apart. The electric field strength gets weaker. So really, that's what this all means here. So we'll just do the positive charge as well. Now, the shape is going to look exactly like, but in this case, if you had a positive test charge, say at that point just here, it would be getting repelled, so it would be getting pushed away. So these are the fields for the electric field for an isolated positive charge.